Foundation models for embodied decision-making agents, part 14. I want to talk a little bit more about a concept that I came across in Jitendra Malik's recent presentation. I discussed it actually in the previous episode more in detail. What I want to focus on here is on the compound effect of technology. What that means is, in particular, with Malik's presentation, he mentions the 3Difying of images as a necessary condition for robotics to sort of make the next leap. And what he means with that is that once we 3Dify images, we can then simulate reality in 3D and then have robots learn in sim and then solve this sim to real problem and therefore have a massive amount of opportunity to try and error and that way learn generalized robots. And there's two things that matter when it comes to simulation. One is the current techniques that have been very promising in optimizing behavior are all circling around reinforcement learning. Now, reinforcement learning, going way back to the cake by Jan LeCun, has always been considered a technique which is, whilst powerful, very cumbersome. In other words, it just takes a lot of errors to learn something. There's very little signal in the noise, or in plain English. You have to fail so many times until you actually figure out how to do something. That's not very feasible in reality. So researchers like Malik and many others are navigating towards some sort of simulation, whether it's actual simulation or I would argue even offline reinforcement learning, which is what say Sergey Levin is advocating. They're all kind of in the same realm, which is you want to collect a large data set of action state pairs and learn from that and have some sort of pre-training. That's the key, right? You don't wanna let the robot go. Let's say the Airbnb test, which is you're entering a completely foreign apartment. You have no idea where things are, and now you as a human, you have to find the the cutlery, right? What are you gonna do? You're gonna look for the kitchen. You're gonna look for the drawer, etc. The robot has, ideally we want a robot that can do the same thing, right? You put that thing in a totally strange environment, never been there before, and then, go, slice me a sandwich or make me a sandwich, right? What's the robot gonna do? It's gonna find the kitchen and so on and so forth. Now, in reinforcement learning, as we know it now, there's a lot of nuances in reinforcement learning. There's model-based, model-free, there's policy and off-policy. Let's say if we take the canonical reinforcement learning method, which is model-free on-policy, which just means that the agent literally keeps trying and failing, and every time it does something that gives it a little bit of a reward, it keeps improving its behavior. It has no model of the world, so it's what's called model free, and it's on policy in a sense that whenever it does something wrong, it updates its weights, and whenever it does something right, it updates its weights. It updates its parameters. So it learns by doing on the spot. This is the equivalent of when most humans learn how to ski or surf or play football. You don't go to the simulator. You don't read about these things. You just start doing them. When I started jiu-jitsu, I just started doing it. So that was off model free on policy. That's how I learned jiu-jitsu, particularly jiu-jitsu the hard way. Got taught many times before I figured out how to defend myself. So in that sense, we humans can do that, and um, robots cannot. That's Jitendra Malik's main argument in the most recent talk he gave. There's a link in the show notes to that talk. There's also a whole episode discussing the talk. I think it's just a previous episode. Just go on our website and check it out. Anyway, what I want to talk about today here in this episode is the concept of compound technology, which means that we have some innovation that is a predecessor for follow-up innovation, and technology compounds on each other. I think, to me, the canonical example is actually the self-driving car. The self-driving car was launched, let's say, officially in the sort of early 2000s with the DARPA challenge. Now, researchers will tell me, no, that's wrong. There's been self-driving car attempts in the 70s and 80s, and yes. But I would say the main difference between the self-driving car concept in 1980 and 2006, in my opinion, is one is just compute power, but also algorithmically things have changed. The 70s were still driven by control theory. And without getting too technical, you can think about it this way. You have a robot that takes inputs and then has some sort of translation function, or the planner, the actual technology that makes the robot do things. Call it the planner, the weights, the matrix that makes the robot turn left versus right. Like whatever initiates an action with the robot, that thing, let's call that matrix A. This matrix A in traditional control theory is a fixed matrix. It's analytical. It's derived. Engineers think about really hard and then come up with some sort of translation matrix. In the modern area, this matrix is being learned. Now, in the early 2000s, that learning was still somewhat rudimentary in a sense that it wasn't end-to-end data-driven. It was, littered. I should use the word littered. There was a lot of symbolic logic, things along those lines. I don't want to go too much into the history of AI because it's not really relevant. I think AI itself has been a try and error for 50 years, and we've just come up with stuff that works, and whether that is the optimal solution to the problem or not, who cares? It just works. To paraphrase Dieter Fox, I don't care at this point. Maybe it's my age, but I just want these things to work. That's how I feel as an investor in Tesla. Whether Tesla is using the most recent state-of-the-art models and technologies and architectures to make FSD 12.3 work, I don't care. All I care is that it's working. I would say amazingly well. I even had a Move 37 event recently where it did something that I would not have ever done. Okay, this is a tangent now, but please let me indulge because I found it amazing that this model is able to do it. So what happened is I was in a very tight spot. It was one of those situations. Anybody who lives in California knows what I'm talking about. You're on an X-lane highway and you want to change lanes. You're stuck. There's a car in front of you. There's a car in the back, and on your left, people are just going. Of course, nobody would ever, let you, get in that faster lane. People are very territorial about this in California. Now, what my car did is it squeezed in there. And the way it did it is first it had very little space to turn. So it optimized that space. Basically, it made a turn on a very, very tight angle and it squeezed itself in. And I think the reason the car was able to do this is because it has very good measurements of where it is. It has good measurements of where the front car is the back car and where the car on the left, which is coming, is in terms of speed and stuff. I think better than I have, and therefore it was able to do it. So Move 37, maybe it's not the classical Move 37 that it did something that humans would never have thought about, but it's more like a move a la David Scaramuzza. in his drone experiment where the robot did something that the human would have deemed way too risky. The robot did it because it has better technology to measure the actual optimal angle and things like that. So back to Tesla, whether they did this now using quantum physics underlying the model, or whether it's end-to-end, learned, I don't care. It just works, and that's the key. So now back to Jitendra Malik and the compound value of technology. Now, in the early 2000s, we had the first boost of the self-driving car, and the self-driving car back then was driven by what's called sensor fusion, which is basically, think about it, if you take a Waymo car today, or even some of the other, but let's just use Waymo, and you look at visually, they look funny because there's a lot of stuff on them, lots of sensors. And they use sensor fusion, which, like the word says, they just fuse sensors together and then sort of learn from there, and that's it, and they go on. Now, what happened in the late 2000s, early 2010s is ImageNet. And what ImageNet did is basically launch computer vision as a field from academia to the real world, or the transition from academia to technology happened. And convolutional neural nets became very popular for various reasons to solve computer vision. Andrej Karpathy, one of the proponents of computer vision, one of the leading researchers in computer vision, joins Tesla because Tesla is applying computer vision as a sole sensor for the car. And with the advancements of computer vision, full self-drive becomes possible. There's a couple of other innovations that are necessary to get us to 12.3, but it was computer vision that was necessary. Now, this is another tangent. Please let me indulge here. There's a professor at the University of Chicago by the name of Neil Shubin. He studies prehistoric biological evolution, stuff like that. And he wrote a book about a species that went from water to land. And the big question that he's trying to answer is, how is it even possible that organisms transition from water to land? Think about it. Like, you have whales, sharks, barracudas, sea otters, medusas, all that stuff that lives in the water. How was it? Well, who came up with the idea to transition to land, right? It's crazy. And I've written and read about this a lot. There's a bunch of episodes way back. One of our early episodes at the Not Even Wrong podcast covered this stuff because it's a beautiful analogy to the way markets work, to the way disruption works, to the way evolution actually works. And evolution, whether it's Darwinian evolution or what I call Clayton-Christonian evolution, which is the same concept, it's the idea of disruption. Clayton Christensen formulated the idea of disruption, which, in my opinion, is just another word for evolution. It's just applied to entrepreneurship and business. And we have to look at disruption the same way we look at evolution, which is it's not about survival of the fittest. It is finding your new niche. The way you find your new niche is by having some sort of technology that lowers the cost to survive in a particular biotope. Now, in biology, this typically means you need less energy to get food and mate and reproduce than others. That's how you survive. And in business, it means lower cost. I've said this so many times in this podcast. To us, a company is defined by its cost structure. Whether you are competitive or not depends solely on your cost structure. You might say, well, what about ExxonMobil? What about Pearson? What about AT&T? They have monopolies. They have scale. They have blah, blah. Yes. But it's irrelevant for us investors. And this is by definition. Maybe this is a Goodalian sort of incompleteness problem here. We define ourselves as investors who only care about disruption. We don't call that word because it's being misused, but we're investing in fundamentally new concepts and engineering practices. That's what we look for. So in that sense, we only care about companies that actually follow the evolutionary process of finding new niches and developing markets in those niches. And the way they do this is by compounding technology. This is the key message of this episode, right? Compounding technology is like what Tesla did with computer vision. Compounding technology right now with robotics is 3D-define 2D images. What do I mean by that? We believe that the future of robotics is going to be solved with reinforcement learning. And like I said in the beginning of this episode, reinforcement learning has the problem of having very little signal to noise. In other words, you need to do a lot of trials to get something learnable. And you can do that in the real world with lots and lots of effort and cost, this and that, or you can do it in sim. And I think in simulation, which means in sim, is also much more, suits itself much better for the embodiment problem. So what you can do with a simulation is, for example, you can have a robot learn in simulation, try and error, and then adjust for sort of generalize, almost virtualize the actual embodiment. So that means that whatever you're learning can be abstracted away some sort of layer. I'm not 100% sure how this can be done technically. I wouldn't be able to code it up on GitHub, but conceptually, what I mean is you could learn how a robot grasps stuff and then make it sort of API-able to any kind of embodiment. That's what I mean. So as long as it's in software, as long as this is in the virtual space, embodiment is not so important. So conclusion, again, of all of this is we need simulation. And I think Jitendra Malik, I met him about 6 months ago at Mars in Stanford. He said that the most exciting thing in his research lab is when things happen in simulation. Now, having said that, we believe that 3D-defined 2D images is important for simulation, in particular for robots. It's not so important for self-driving. It's useful, but it's not key, right? When you drive, let's say on my screen right now, I'm actually driving FSD 12.3. Right now, it's driving me. I'm seeing cars around me. I'm seeing the road signs, bikes, all that stuff. And whether that is a good representation of the 3D situation or not doesn't matter as much. What we really need is a good idea of geometry. We need to have a good idea of physics. In other words, the car needs to have a good sense for when something's coming, how fast it's coming. But whether there is a good representation of the 3D structure, the material structure, the actual look, the feel of materials, things like that, doesn't matter for the car. The main job of a car is navigation. It's not grasping, it's not touching anything. Actually, the self-driving car is totally trained not to touch anything. So that's exactly different with a robot. Most robots the purpose of robots is to touch things, whether it's warehouse robots moving stuff around, or your home robot, or an elderly help robot. It's hard to think of a robot that has any kind of purpose without having to touch stuff. So as soon as we interact with the environment along those lines, so meaning touching, you need a much better 3D representation. So 3D-defined 2D images, according to Jitendra Malik, is the key towards robotic simulation, which is the key towards robotics. And then once we have enough data in sim, we can build robots that can collect data, and then we can go from there and bootstrap ourselves. Now, before I go further, let me just elaborate a little bit why this is so important. Another thing from the Malik presentation is the fact that he said that basically everything in robotics is now transformer-based. And if you want to be transformer-based, you have to do two things. You have to do what OpenAI is doing, and Llama and all these people. One is you have to have a massive amount of data that is somehow storing a bunch of tokens in a way that it represents reality. So in the case of LLMs, we tokenize text, and then we run these models, these training models, which their main job, the models, their job is to 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 do unsupervised to do unsupervised learning, to just classify all that stuff. It works. I walk on the beach, I play on the beach, I enjoy the beach. Those things belong together. I suffer on the beach. It's so freezing. They don't belong together. But the word beach can come here and there. So where does it come? Depends on the words before and after. The word suffer and beach usually mean the weather sucks. The word enjoy and beach usually mean the weather's nice. So what unsupervised deep learning does, it classifies all these things, learns. Now the classification itself is the pre-training, and then we use reinforcement learning to fine-tune the models so they can give us a nice chat wall, or they can summarize Shakespeare in a nice way and so on. Now the same architecture can be used in robotics, but for that we have to have some sort of pre-trained multimodal model. And this is the gist of this episode. The gist of our work is to um, understand where the science is and where the technology is in terms of using transformer architectures for multimodal training for robots. This is really the key. We believe that both our investments that we have two large positions, which is Tesla and NVIDIA. There's other investments, and please don't follow our advice here, follow your own research. We are just, you know, telling people what we own and how we invest for transparency's sake. But this is not meant to solicit any investors, so please do your own work. So our positions are geared towards real-world AI, and real-world AI can be solved with predefined images and then use that for simulation and then build a robot fleet and then go from there. The difference between full self-driving robot is that the full self-driving is not touching things versus robots are supposed to touch things. And when you're supposed to touch something, by definition, you need to understand, have a better understanding of the 3D world. Now, to finish this episode, I want to maybe just lean back a little bit, get a little bit philosophical in terms of what does this actually mean to have a compound effect of technology. And again, back to Neil Shubin's idea. So we had these creatures that cross from water to land, and then maybe learn how to crawl, and then from crawling, learn how to walk, and then from walking, learn how to run and hunt and eat, get more protein, and the rest is history. So we need predecessors, we need limbs in a fish that might not even be that useful in the beginning, but turn out to be crucial at some point in conquering land. So if we take this to Tesla right now, whether Tesla is good at predefining 2D images, maybe it doesn't really matter for their quarterly sales. But it's my conjecture that eventually it will be the crucial differentiator between Tesla and everybody else in terms of building a fleet of humanoid robots. Because 3D 2D images is going to help Tesla train their robots in sim, and then the sim to real translation, actually, according to Jitendra Malik, is not even such a big problem. It can be solved, and we've seen that also in David Escaramuza's drones. The sim to real translation wasn't the bottleneck. It's not easy, but it's not the bottleneck. So to summarize, compound effect of technology is it's a beautiful thing. It's what disruption is really built on. It also actually is sort of the cousin of the innovation stack, because what Jim McKelvey means with the innovation stack is exactly that. It's the compound effect of, in his case, solutions to problems. But you could argue that most of the solutions to problems are technologically anyway, so in that sense it's the same. So what Jim McKelvey is talking about is you solve, a couple of maybe easy problems, and then you keep creating new problems, you solve them, and then you create them out by iterating over problem space to the point where competitors have a really hard time just stepping in and replicating all you did. Let's use another example with Tesla. Tesla has iterated on the battery front, on the operating system software from for the car, on the actual software-defined car from FSD is just the canonical example. But there's a lot of other things that Tesla is innovating on. Just all these software updates we're getting all the time are testament of that. And for competitors, it's really hard to step in. I mean, that's why we had such timid response from competitors. You know, whether it's BMW, Volkswagen, NIO, it's hard. I mean, we should never neglect competition. There's certainly companies out there that are aggressively going after Tesla, but it's just hard to just step in today and compete with somebody who's been solving problems for the 10 plus years, and because it's not just one problem, it's a compound effect of solving problems, creating new problems, solving problems. Same, you can replace problem with the word technology and say you create new technologies, and the moment you create new technologies, you build upon those technologies. So, example, you solve computer vision, and then you build a self-drive stack on top of that, and now you have a planner, end-to-end learning, which is based on computer vision. So for people who've been doing sensor fusion, this is they almost they have to go back to the drawing board, start from scratch, and that's really hard. So to summarize, the compound effect of technology, in our opinion, is the key to disruption. It's the key to wealth creation, because that's where the scaling actually happens. The scaling doesn't happen by some genius having an idea and developing a technology and then here we go. It is carefully coming up with new technologies, failing a lot of times, but sometimes some of those technologies actually make it to the marketplace and they keep growing and they create their own problems and solutions. And from there, we have a compound rate of growth that eventually allows companies to generate these gigantic returns that normal companies, if you will, are not able to achieve. And we believe that 3 to 5 2D images is the next big domino to fall. Once that is solved, simulation will become much, much more feasible for robotics. And with simulation being feasible in robotics, we have an opportunity to really penetrate new avenues, penetrate many new avenues of potential, whether it's again home robots, and we believe that's also the beginning of the unsupervised intelligence that we spoke about, which is a robot that eventually learns how to not just solve problems and execute tasks, but also define its new tasks.